Okay, so for this lab, we're going to be calculating Planck's constant using LEDs with Jason, Josh, and Nick. So for our abstract here, we have Planck's constant represents the relation between how much energy a photon carries and the frequency of its electromagnetic waves. It is approximately equal to 6.626 times 10 to the negative 34th joules seconds. Using 6 LEDs and a spectrometer, Planck's constant can be found. The value that was calculated during this experiment was 6.445 times 10 to the negative 34 joules seconds, which gives us a 3% error. Our introduction here, Planck's constant tells us how the energy of individual photons relates to the wavelength of their emitted radiation, or light. During this lab, we were able to use the tools given to us to measure the wavelength of each LED. With each wavelength determined, we then were able to plot an activation energy versus frequency graph for each LED given. Once plotted, we will be able to determine Planck's constant by abstracting the slope from each LED in the graph and multiplying it by the charge of an electron.
So for the procedure, a circuit was built to be able to measure the voltage and current going through an LED. The voltage was changed from 0 volts to 5 volts in 0.1 volt increments. This was repeated for 6 different LEDs. Once that was completed, the power supply was set to 5 volts. The spectrometer was placed near the LED to find the wavelength and intensity of each of the 6 LEDs. So the materials we used in the experiment were a power supply, a breadboard, resistors, wires, 6 distinct LEDs, lab press mini, current probe, voltage probe, and a spectrometer. And these are the equations we used. EG equals HF, EG equals EVF, VF equals MF, M equals H over C, H equals EM, and F equals C over lambda.
For our first part of the experiment, what we have is a potential versus current. This was done, and this particular graph is for the violet LED. What you see is 50 different measurements of the changes in 0.1 volts. So from that, you can see that there is a straight line that's right here. From that straight line, we found out what the slope would be right here. In order to calculate our forward voltage, what we had to do is set this equation, set our y to 0. Once we set that to 0, we can then find these values right here. Moving on to the next one, what we have is our spectrometer. This is what we use a spectrometer. This is the same for the violet LED as the previous slide. For this, it's a little bit hard to see on the camera, but there is a peak point right here, and at that peak point, we measured where we saw where the wavelength was. That would be where it was the most intense. From finding out that wavelength for each of the LEDs, use the equation C over lambda to find our frequency, and those values are stated right here. Moving on to our data analysis, what we had to do is we measured frequency versus our forward voltage. For this, what we ended up finding out was, what we needed to find out was our slope, which was 4.028 times 10 to the negative 15th. Then we use the equation H equals E times M, which is our slope, E being the electron voltage, and we calculated 6.445 times 10 to the negative 34 joules per second, joule seconds compared to the actual value, which is 6.626 times 10 to the negative 34 joule seconds.
So, sources of error in this experiment were no stand was used to hold the spectrometer, which could have caused inconsistencies in the readings. Reflections off of the LEDs could alter the readings and skew the results in the direction of, let's say, the lights, because it give off light. And changes in voltages could only be done in 0.1 volt increments. Smaller increments could potentially give more accurate results.
And for our conclusion here, this lab was a fairly simple lab. To find Planck's constant, we first found the activation energy of each LED using the current and the voltage probe. Once the activation energy of each LED was found, we then were able to find the wavelength of each LED with the use of the spectrometer. Then using equation 6, we were able to abstract the frequencies from each LED. We then plotted a frequency versus activation energy graph with a best fit line running through all the points. We then abstracted the slope from the best fit line and used equation 5 to solve for Planck's constant. We ended up calculating a Planck's constant of 6.668 times 10 to the negative 34 joule seconds, which when compared to the true value of 6.626 times 10 to the negative 34 joule second, that gives us a 3% error.